All right, let's dive in. Today, we are talking about a classic foundational tool in machine learning called logistic regression. Now, I know the name sounds kind of technical, maybe a little intimidating, but don't let it fool you. At its heart, it's actually a really simple and powerful idea that helps us answer some of the most basic questions out there. Simple yes or no questions. I want you to just think about your email inbox for a second. Every single day, there's this little guardian working behind the scenes, and for every single email that comes in, it asks one question. Is this spam or is it not spam? That simple binary choice is exactly the kind of problem we're tackling today. And you know what? Once you start looking for it, you see this kind of question literally everywhere. For an online store, it's, will this customer actually buy the product? For image recognition, it's, is that a cat or a dog? In school, it could be, will this student pass the final exam? And in medicine, it gets really serious. Will a patient respond to this treatment? These aren't just little games. We're talking about decisions with huge real-world impact. So that brings us to the big challenge, right? How in the world can we teach a machine to make these kinds of critical choices? How do we get it to look at a whole bunch of information and then confidently sort it into one of two buckets, a yes or a no, a cat or a dog? Now, if you've been around machine learning a bit, your brain might immediately jump to an answer. You might be thinking, aha, linear regression. We'll just draw a line through the data. And that's a great instinct, but not so fast. For a simple yes or no question, a straight line just isn't the right tool for the job. It's actually designed for a totally different kind of problem. And here's the fundamental difference, laid out plain and simple. Linear regression, on the left, it predicts a continuous number. Think of it like predicting the price of a house. It could be any value, from 50,000 to 5 million. But logistic regression, on the right, does something way more specific. It predicts a probability, a number that is always stuck between 0 and 1. It's not answering how much, it's answering what's the chance. And that brings us to the really cool part, the aha moment of logistic regression. It's this genius little mathematical trick, which I like to call the probability squeeze. This is the secret ingredient, the key that turns a regular line into a powerful decision-making tool. So what is this secret ingredient? It's called the sigmoid function. And you could just think of it as a probability converter. Its one and only job is to take any number you throw at it, big, small, positive, negative, doesn't matter, and translate it into a sensible probability between 0 and 1. It has this cool S shape that squishes really big numbers toward 1 and really small numbers toward 0. Okay, so let's walk through how this actually plays out. First, the model looks at all the data it has, say the words in an email, who sent it, things like that. And it cooks it all down into a single score. So, imagine the model chews through all that data and spits out a number. Let's say 4.8. Now, what on earth does 4.8 even mean? Well, on its own, not much. It's not a percentage, it's not a probability, it's just a raw score based on the evidence. But then we take that raw, kind of meaningless score and we feed it into our magic sigmoid function. And this is where the transformation happens. The function takes that 4.8 and just squeezes it into that nice, clean range between 0 and 1. And boom, out the other side comes a number like 0.99. Now that is something we can work with. The model is basically screaming at us, hey, I am 99% sure this thing is spam. And just like that, we went from a weird, abstract score to a confident, useful prediction. Okay, so that's the what. We know how it gets the probability. But the bigger question is, how does it learn to do this? How does it get smart enough in the first place to know where to draw the line between a yes and a no? The answer is something called a decision boundary. And you can literally picture it just like that, an imaginary line in the sand. The entire goal of the model during training is to figure out the perfect place to draw that line so that all the spam emails end up on one side and all the good, legitimate emails are on the other. It learns where to put this line by looking at thousands and thousands of examples. So how does it know if its line is any good? It uses a sort of grading system. This is called log loss. And what's really clever about it is that it doesn't just penalize wrong answers. Oh no, it penalizes overconfident wrong answers. So if the model shouts, I'm 99% sure this is spam, and it's wrong, wham, it gets a massive penalty. It basically teaches the model not just to be right, but to be, well, not too cocky about its predictions. And this all fits into what we call the training loop. And it's pretty straightforward, really, just a cycle. First, you make a prediction. Then you check how wrong it was. Then you figure out how to do a little bit better next time. And finally, you nudge your decision boundary just a tiny bit in the right direction. And then you repeat over and over and over again, thousands of times, getting a little smarter with each loop. Okay, so we've been pretty deep in the weeds with the mechanics. Let's pull back up to the 30,000-foot view. Why does any of this matter? I mean, this algorithm is pretty old in tech years, so why are we even talking about it today? Because, and I'm not exaggerating, it is everywhere. It's the silent hero behind your spam filter. It's a key tool helping doctors with medical diagnoses. It's the gatekeeper that decides if a credit card transaction might be fraudulent. It's even helping to figure out which ads you're most likely to click on. It is a workhorse of the modern digital world. And you might be thinking, sure, but what about all the super complex, fancy new AI models? And that's a fair question. The reason this one is stuck around is because it has this incredible triple threat advantage. One, it's fast, like really fast. Two, it's efficient, so it doesn't need a supercomputer to run. And three, and this is the big one, it's interpretable. That means we can actually look inside and see why it made a certain decision. And in fields like finance or medicine, that's not just a nice to have, it's absolutely critical. You know, one of the best ways I've ever heard it described is that logistic regression is the bridge. It's that vital link that connects the abstract world of math to the real world of machine learning algorithms that actually go out and solve problems. If you can get your head around this, you're taking a massive step toward understanding the entire field. It's that important. So I'm going to leave you with a question. Now that you have this new superpower in your toolkit, this ability to teach a machine how to answer a yes or no question, what problem in your world would you solve with it? What's the big question you'd want to tackle first? Something to think about. Thanks for joining me.